In this video, we're going to take a look at regression. Now, least squares regression is a way to fit a line specifically to a set of data. And it's one particular method that is probably the most common. Now, a least squares regression line is also called a best fit line. And that's the straight line that best fits the data. So, for example, if I throw up this red line here, this red line pretty much fits the data about as well as you can from a quick estimate. And it seems like there's a few points above, a few points below, some are close, some are far, but for the most part, it explains the trend. Same thing over here. Now, in some cases, if you have points that are really far away, you might have more points on one side. You just have some points that are almost exactly on the line. But again, you're looking for a straight line that best matches the pattern of the data. Now, whenever you're doing a quick visual estimate like I just did here, you're looking to have it fit roughly about half and half on either side. But when your calculator does it, it will actually give you a much more precise answer than you could ever get in your head. So let's move on. The next major concept is revisiting some of the stuff we looked at when we looked at scatter plots. We had the correlation coefficient, R. And what we're going to do now is we're going to square R. So if R was negative 0.9, R squared would be 0.81. And that has a special meaning, and that's the percent explained. So if we square R and then convert it to a percent, so 0.81 in this case, 81%, it will tell you how much X explains the variation in Y. So that means that whatever our X variable is, when we have a correlation in negative 0.9, X explains 81% of Y. Same thing over here. When R equals 0.7, if you square it, you get 0.49. Convert that to a percent, and you get 49%. So that means that whatever our X variable is in this graph explains 49% of the variation in the Y variable. So it doesn't predict it perfectly. Half of the variation comes from other sources, who knows what, but 49% can be predicted by what X is. And so the higher this, the closer this is to 100%, the better X will predict Y. Now let's go ahead and shoot for some exact answers, and let's go to our calculators. So take out your TI-83s or 84s, and I'll get back to the home screen here. We're going to take this list of XY data, and we're going to punch it into our stat list. So you go to Stat, and again, you go to Edit the first option by pushing Enter. And I have some numbers left over in my list, so I'm going to go up to L1, push Clear, and push Enter, so I can clear those out. And now I'm just going to punch in these values. So I have a 3, I have an 8, I have a 9, and so forth. When I'm done with the first list, I'm going to arrow over to L2 and start doing the same thing. Punch in all of these numbers. Now when you're doing problems like this, I can't stress how important it is to make sure you go back, look at your list of numbers, and make sure they match up with the numbers you were given. Small mistake here whenever you're doing any calculations like we're about to do can really make life difficult for you. So once you have your numbers, you verified they're right, go to Stat, once again, and this time we're going to arrow over to Calc. So we'll hit the right arrow key and go to Calc, and we'll go to the fourth one down, LinReg. So I can arrow down to that, or I can just hit 4. And it'll bring this up on your home screen, and then you just push Enter. Now, for those of you who do not have this R and R squared here, go ahead and skip to the end of the video, and I'll show you how to turn that on at the end. But otherwise, what you're going to look for, R is your correlation coefficient, as you may remember. R squared is your percent explained. And then A and B plug into this line here to get you a line that is your line of best fit. A is the slope, plugs in right here next to X. B is your Y-intercept. So let's go ahead and take a look and take this apart. Here's the information I just got out of my calculator. Our correlation coefficient, once again, is going to be .864, and again I rounded at 3 decimal places. That seemed reasonable in this case, and that's a pretty good fit. My percent explained is r squared, so in this case I converted this to a percent, and it was 91.3 approximately. And what that means is that the number of puppies, since puppies is our explanatory variable here, explains 91.3% of the variation in the number of happy children. So in this goofy little example here, we're saying that puppies, our x variable, explains how many happy children we will have. So puppies cause children to be happy. So in this set of data, this set of made-up data, there is a 0.864 correlation coefficient. Excuse me, my typo there, a 0.956, I read that wrong here, correlation coefficient, we got that right from R, and 91.3% of the variation in the number of happy children can be explained by how many puppies there are. So let's move on with this. The least squares regression line you get by taking your value of A here, and that's our 0.864, this is where it belongs, is the slope here, and we plug that in for A, and then we have our y-intercept, and we plug that in for B, and that's what we got down here. So the least squares regression line is just like any other linear equation. We can solve it for y. Y equals the slope times x plus the y-intercept. Just to break that down further for you here, the slope, 0.864, is rise over run. It's y over x. So that means it's happy children over puppies. So happy children per puppy is the units on the slope, if you're going to put units on it. The y-intercept is just a y value, so it's just the number of happy children. And because it's a y-intercept, just like any other line, you get your y-intercept by setting x equal to 0. So this equation predicts that we will have 4.593 happy children when there are no puppies. So that's where we start off. And then every time we add another puppy, we get 0.864 more happy children. Again, now if you have actual numbers, you're going to have integers, but as far as an approximation for a large number of samples, a large number of trials of this, it could still be a decimal. On our next slide, we're going to take a look at interpolation and extrapolation. Both of these are used to predict values. So interpolation is when you use the best fit line to predict a y value when the x value that you're using falls between the min and the max. Now it sounds a little technical at first, but all that means if we have data with x from 3 to 17, and we want to predict what will happen when x equals, let's say, 10, then we're using interpolation because it's inside the 3 to 17 range. Extrapolation, on the other hand, is when we use something that's outside of that. So let's say we wanted to predict how many happy children we would have when we have 19 puppies. Well, if we wanted to do 19, it's outside of our 3 to 17 range, so therefore that would be extrapolation. One easy way to remember that is to look at the prefix. First two letters of interpolation is in, it's inside the range, and the first letters of extrapolation is x, it's outside of it, it's external. So let's go ahead and make a prediction here. What about when we have 13? Now, 13 is going to be between 3 and 17, it's right here. So 13 is going to be interpolation. However, it doesn't change the calculation. We're going to take that value of 13 and put it in for our x value into our best fit line. So we're going to take whatever our variable x, and we're going to substitute in a 13, because that's our number of puppies that we're using in this hypothetical situation. If we do the math, we just multiply these two together and add that, and we get 15.825. So that means that when we have 13 puppies, we can predict there will be 15.825 happy children. One more example. Let's go ahead and do this with 20. Well, just like 19, 20 falls outside of the 3 to 17 range. So this one is going to be using extrapolation. But regardless of whether you're using interpolation or extrapolation, the calculation is the same. So we take that number, our new x value, times our slope, plus our y-intercept, and we get 21.873. So what that means here is when we have 20 puppies, we can predict that we will have 21.873 happy children. What you're doing when you use interpolation or extrapolation is you take a value of x that you do not know, you plug it into your best fit equation, and you see what it spits out. And that's your prediction. You don't know what you're going to get because you don't have any data on that, but you can make a prediction that it's going to be something like this. The main difference between these two, and the reason why they each have different names, is because interpolation tends to work better than extrapolation. Reason being here is that in this data set, we have a nice clean line, and we have all these points that seem to match up with each other. But once you get outside of the points that we know about, who knows what this line does? Perhaps it levels off or goes down. Because we have no points out here, we don't really know what happens once it goes beyond. So that's why extrapolation is a little bit more dangerous than interpolation. From here, we can say that with reasonable confidence that it's probably going to behave in a linear way. Beyond that, we really don't have good evidence of that. So the farther and farther you get out when you're extrapolating, the harder it is to make a prediction. And the best example of that is when you're looking into the future and trying to predict the future, you can learn things from the past, but you can never be able to predict everything because there's a lot of things you just don't know. So let's do one more example of predicting a value, but this time let's do it of a value that we already have. So let's do it for 8. We already know the value of 8, and we think it's 11. Well, we were told that. But when we plug it into our equation, we get something slightly different. We get a predicted value of 11.505, and that's not 11. Because our original value here, it told us that. So what we're going to do is we're going to call this a residual. A residual is the error in the best fits line prediction of y. Because if the best fit line predicted that y will be 11.505 when x equals 8. But in fact, according to our table, y equals just 11 when x equals 8. So to find the residual, we subtract the actual minus the predicted. The actual value was 11, predicted was 11.505, and so our residual is negative 0.505. And that you can do for any of these values. If you want to find the residual for x equals 12, you would plug 12 into your best fit line, get the predicted value, you would look at your original and say, oh, the actual value is 13, and you take 13 minus the predicted value, and that would be your residual. Now, for any of you who didn't get your calculator to behave right the first time around, you're going to want to quit and go back to the main screen, and if you go to second 0, this will bring up the catalog, and we're going to try to turn that r and r squared back on. So go to D, which is above the x to the negative 1 key, and go down to diagnostic on. So you go down a few, and once you get to diagnostic on, push enter. It'll show up on your main screen, and push enter one more time. Now it should be turned on. So now if you go back to your stat and your calc and hit 4 for your linear regression, hit enter there. This time around, it should have an r squared and an r for you. And that's all for regression.